It's important for us to take ownership of creating a more sustainable manufacturing industry in Europe, especially through additive manufacturing. Our goal in the EU-funded InShaPe project is to achieve a faster, more cost-effective and eco-friendly powder bed fusion process of metals. Powder bed fusion is an additive manufacturing process in which layers of material are melted with a laser to form the final shape. Currently, the powder bed fusion process is too rigid, too expensive, and not resource efficient for many applications. This is the motivation for the InShaPe project. As a consortium, we are addressing these challenges by using two technical innovations. The first one is the beam shaping technology, where we customize the energy input, and the second one is multispectral imaging. We aim to achieve a production rate that is 7 times higher than the current state of the art, while maintaining over 50% cost reduction, 60% less energy consumption, and 30% less waste. This will transform the additive manufacturing industry in the future. 11 partners from 7 European countries and Israel are working together towards achieving this goal in 3 years. Experts in powder bed fusion, multispectral imaging, AI, and 4 use case partners are included. One of these partners is EOS, represented here by Isabel Rodea and Markus Birk, who will explain to you the technical innovations of the project.
The first one is a new light engine. It is a new bin shaping technology, which is proprietary from EOS. And the second one is a new process monitoring system, which is called multispectral imaging.
So beam shaping is a technology for metal laser powder bed fusion that allows us to flexibly change the laser beam shape at will. This technology opens a wide range of new parameter windows, as we can flexibly adapt the laser beam shape to, for example, the material and also the part geometry of individual applications. We have many different advantages if we do beam shaping. For example, we can increase the stability and robustness of the printing process, as we have more control over the heat distribution and the heat flux in the printing process. We can, for example, also print new materials, as we can specifically tailor the laser beam shape to the solidification behavior of different materials. We can also adapt material properties in a wide range and also adapt them specifically for different applications. And at last, we can also increase the printing speed, as we now have new process options and more control over the printing process overall. When we do beam shaping, we want to know a lot about the melt pool and the temperature of the melt pool. And with multispectral imaging, we have a unique monitoring system that allows us to measure absolute temperatures. In our prototype machine, there are 2 camera systems installed. One on a micro basis, which records the temperatures of the melt pool and a small region around it. And also a camera system on a macro basis that measures the whole layer of the printing process. Besides of that, we also develop a new spectral filter and algorithms to evaluate this recorded data. And this will then be combined into a feature-based AI algorithm that will allow us to control the process on an automatic basis at the end. The current status is that we have implemented these 2 technologies into an industrial additive manufacturing system from EOS. And we're currently validating different materials and processes. And we expect to set new machine standards with these innovations in terms of productivity, flexibility, efficiency, and also achieve a considerable cost per part reduction.
So the next steps are, we're going to test this technology with our 4 industrial partners. And finally, we will go into commercialization. About the use cases, we have our industrial partner, Oerlikon, and he's going to explain you what it's all about.
A high manufacturing cost is a major barrier to industrialize products with additive manufacturing. In Project InShaPe, we aim to reduce the cost of the parts by affecting various factors, including print time, support structure, residual stresses, microstructure control, and stability of the process. Significant changes to these factors are difficult without new technologies such as beam shaping. In Project InShaPe, we will demonstrate this through the use of 4 use cases: an impeller, a chainsaw cylinder head, an industrial gas turbine part, and a combustion chamber for a rocket engine, each with defined development goals. Beam shaping technology affects almost the whole value chain. It reduces post-processing, lowers energy consumption, and minimizes waste generation. These effects improve the business case of all AM parts.